In this video, I'm going to go over using the double angle and half angle formulas. So first, for the double angle ones, I'm going to go ahead and derive these from the previous formulas that we did in 7.2, and then use them in a few problems. And then I'm not going to derive the half angle formulas, but I'll show you what they are and how to use them to find the sine or cosine or tangent of angles that are actually cut in half. Okay, so we're going to start with the double angle formulas. All right, and these are essentially just special cases from our formulas that we used on the last one, where we talked about looking at adding the sum and difference of two angles with sine and cosine. So this is the special case where alpha and beta, or A and B, are actually the same. So what we're going to do is we're going to actually set this also equal to theta and replace the alpha and the beta with theta, and you can see what's going to happen to these formulas. So it'll be the sine of theta plus theta equals the sine of theta times the cosine of theta plus the cosine of theta times the sine of theta. So what happens is we have sine of theta plus theta, which gives you 2 theta. That hopefully should make sense. We're talking about double angles, so times 2. And if you look, even though the order is different, right, it is multiplication. So because multiplication is commutative, that these are actually the same thing. So we write it as equal to 2 times the sine of theta times the cosine of theta. So this is one of the first double angle identity. Let's do the next one. Same thing. Replace the alpha and the beta with thetas. So I have cosine of theta times the cosine of theta minus sine of theta times the sine of theta. So similar idea to what we did in the previous one. This becomes 2 theta. But if you notice, we have cosine times cosine, which is going to be cosine squared theta. And then minus sine times sine, which is sine squared theta. All right, so that is our second one. Now, because of one of our Pythagorean identities from the very first lesson in this unit, we can actually take this cosine of 2 theta and rewrite it to have 2 extra ones. Okay, so we're going to use this Pythagorean identity from the very first lesson on this unit. Sine squared plus cosine squared equals 1. So if we manipulate that, I don't care the order which you do this. All right, I'm going to first manipulate the cosine squared. All right, so if I rewrite cosine squared, that's the same as 1 minus sine squared. So this becomes 1 minus sine squared theta minus sine squared theta. If we take the parentheses off, we have 2 of the opposite of sine squared theta, so that's equal to 1 minus 2 times sine squared theta. All right, do the same thing, but this time replace the sine squared using our Pythagorean identity. So copying on the cosine squared. And it's going to be minus, and sine squared is the same as 1 minus cosine squared theta. If you distribute, you'll have a minus 1, but subtracting a negative cosine squared theta is actually another positive. So we get 2 of the positive cosine squared thetas minus 1. So again, I don't need you to know the derivation that we just did for these different formulas. I will be asking you to do a formula quiz where you have to memorize these formulas. All right, last one for tangent. Again, we're going to replace theta for A and B, or alpha and beta. So tangent of theta plus theta is equal to tangent of theta plus tangent of theta over 1 minus tangent theta times tangent theta. So again, we have our double angle, right? 2 theta equals, that's going to be tangent theta plus tangent theta, which is 2 times the tangent of theta, over 1 minus tangent times tangent, which is tangent squared theta. All right? So again, not worried about the derivation, just need to make sure you know all of these formulas. And now we're going to do a couple examples to help us figure it out. So This first one says, given that the sine of alpha is 5/8 with, this is the angle or alpha, is in quadrant 1. So quadrant 1. All right, we've got quadrant 1. All right, there's our alpha. Find the cosine of 2 alpha. So the cosine of 2 alpha is one where you've got 3 different options. Okay? So remember, you've got 3 options here. And when I look at what I'm given the sine of my angle. So I only want to choose the option that only has sine, which is the second option here. So that's equal to 1 minus 2 times the sine squared of alpha. All right, so I'm going to plug that in. 1 minus 2 times the sine of alpha is 5/8, and we're squaring that. That's 1 minus 2 times 25 over 64. 1 minus, that's good. That 2 over 64 will reduce to 32 in the bottom, so 25 30-seconds. And if you were to change the number 1 to have a common denominator of 32, you get 32 30-seconds minus 25 30-seconds, which will give us 7 30-seconds. And that's it for that first one. Okay, let's do the next one where we're going to use one of our, I guess really not one of our things. Oh, sorry about that. Where we're going to use, come back. There we go. We're back. Where we're going to use our understanding of algebra to help us make this a true statement. So we know it's true. Let's verify it. What I notice on the left side, it's a little bit more complicated. I've got 2 trig ratios raised to the 4th power, but it's connected by subtraction. So this is actually, when I look at that on the left, I'm thinking this is dots, the difference of 2 squares. So I have cosine squared theta minus sine squared theta times cosine squared theta plus sine squared theta. And that makes me very happy now, because if you look back at the one we just used before, right, sine squared theta plus cosine squared theta is one of our Pythagorean identities, which is the same as 1. All right, and even though the order is a little bit shifted because it's addition, which is also commutative, this right here is going to be equal to just, I guess I should draw it all the way over, equal to 1. All right, so now I just get to bring down cosine squared theta minus sine squared theta, and this is one of the new identities from today, where the cosine of 2 theta equals cosine squared theta minus sine squared theta. So if you do the very last step, right, we replace this with the cosine of 2 theta, right, which equals what we wanted to. All right, so that was just using some old identities and some new ones in the same problem. Okay, so the last part of this lesson, and again, as I mentioned at the beginning, I'm not going to prove these half angle formulas. I'm just going to use them. And what you should notice in all of these, at least the first one of tangent as well, is they all have plus or minus with them. You're not going to do plus or minus. You're going to choose either the positive version or the negative version, but we have to make sure we know what quadrant our half angle is going to end up in, and that will tell us if the ratio that we should use is positive or negative. So let's try this one. We're going to do 3 different ones. We're going to do sine of alpha over 2, or 1/2 alpha, the cosine of 1/2 alpha, and the tangent of 1/2 alpha. So the first thing I notice is it says that tangent of alpha is 8/15, and alpha lies in quadrant 3. So if I were to draw this, right, it's in quadrant 3, right, and here is our alpha. And it says tangent, which is opposite over adjacent, so opposite side 8, adjacent side 15. But what we should notice is that we're going down in the y direction and to the left in the x direction. So they're both negative. The reason that kind of gets masked is because when you divide -8 over -15, you get a positive fraction. So that's why it can be a little tricky there. So let's find the hypotenuse, or my letter R, by doing -8 squared plus -15 squared equals R squared. So 64 plus 225 equals R squared. So that's going to be 289. And if you don't know the square root of 289, you can look it up in a calculator, but it's 17. So this is 17. All right, now R is always positive, so don't need to worry about that. So now, before I start doing these, the last thing I want to check is where would the angle alpha over 2 reside or terminate? So it said that alpha was in quadrant 3. So if I draw a quick little sketch here, in quadrant 3 would be between 180 degrees and 270. So what you do is you divide both of these numbers by 2, and that will tell you kind of the range of values that we can have for our alpha divided by 2. So we have 90, right? 180 divided by 2 is 90. 270 divided by 2 is 135, which is right here. So really it's this kind of area, right? These angles between 135 and 90, which you should notice is that is in quadrant 2. All right, so we'll use that information to help us answer these 3 questions. So number 1 says the sine of half of alpha, or alpha over 2. So I'm going to write down my formula, which is the square root of 1 minus cosine of alpha over 2. Now, before I start plugging in stuff, decide, is this going to be the positive version or is it going to be the negative version? And what I notice is we're in quadrant 2, right? We decided at the end of the day we're in quadrant 2 for our half of an angle. So if we're in quadrant 2, right, all students, S for students, S for sine. So this will be the positive version. All right, so let's plug in cosine of theta. So 1 minus cosine, I guess I should say alpha. Cosine of alpha is going to be adjacent side, so -15 over the hypotenuse of 17. So minus -15 17ths all over 2. Then I'll do that again. All right, and which is 1 minus a negative is really addition. And I want to get a common denominator, so 17 17ths would be 1. So 17 plus 15 is 32 17ths, right? And we're dividing by 2. Again, I'm never going to divide by that 2. I'm going to go ahead and multiply by the reciprocal, which is going to give me times 1/2. The 32 divided by 2, when I look diagonally, is going to make the square root of 16 17ths. I do know the square root of 16, that's 4. And I don't know the square root of 17. So this is the answer. But if you get a common, or I should say, if you rationalize the denominator, you get positive 4 times the square root of 17 over 17. So this is my final solution. All right, and notice we use the positive version, right, the whole time. All right, so that's our final answer there. Let's do 2. Cosine of half of alpha, or alpha over 2. All right, remember, I'm going to copy down the formula, 1 plus cosine of alpha over 2. Again, decide, we're in quadrant 2 where sine and cosecant are positive, so cosine is actually not positive. This will need to be a negative. So the opposite of 1 plus the cosine of that, which is -15 17ths all over 2, which is equal to the opposite of. So 17 17ths minus 15 17ths is 2 17ths. And we're dividing by 2, which is going to be multiplied by 1/2. The 2 over 2 will cross out and get me 1 over 17. I do know the square root of 1, right? Square root of 1 is 1 over the square root of 17. Rationalize the denominator, and you get the opposite of the square root of 17 over 17. So that's the final answer for 2. Let's do the last one, 3, which I believe is tangent of half of alpha. All right, so tangent of half of alpha is going to be plus or minus 1 minus cosine theta, or alpha, over 1 plus cosine of alpha. All right, let's decide. We're in the second quadrant still. Again, so this still needs to be a negative. Only sign was positive. Plug in the stuff that we know. We actually did these already, right? If you remember, we had 1 minus the cosine of alpha, which gave us 32/17 from the first one, divided by 1 plus cosine of alpha, which gave us 2/17, 17/17 plus negative 15/17, which is 2/17. So if you multiply by the reciprocal, the 17s will cross out. I guess I'll just show the work. So times 17 halves. We get the 17s cross out. 32 divided by 2 is 16. And the square root of 16 is 4, but don't forget to bring down that negative. All right, that's it for those half angle identities. Let's do one more, and we'll just, same thing essentially, but just only one. All right, so it's telling me, the first sketch, that alpha is in quadrant 4. So somewhere over here is going to be our alpha. It says the sine, which is opposite, so negative 4, over hypotenuse of 5. And I already know this then must be 3 for x. And we're moving in a positive direction in the x direction. If you needed to do the Pythagorean theorem, you can. All right, so we need to find the exact value of cosine of half of alpha. So again, if it's in quadrant 4, that's between 270 and 360 degrees. So let's cut those in half. If we divide them by 2, we already know 270 divided by 2 is 135, which is in the second quadrant. And 360 divided by 2 is 180. So somewhere in between here, right? And that is in quadrant 2. So just like the previous one, we'll be focused on quadrant 2, where if I do cosine of an alpha or angle, whatever, in quadrant 2 is going to be negative. So I'll make sure to choose the negative version of my half angle identity. All right, so it's going to be the negative version of 1 plus the cosine of alpha over 2. So let's plug in what we know. We know that the cosine is going to be the adjacent side, so 3 over the hypotenuse of 5, so 3/5 over 2. Let's add the tops. So we get 1, which is really 5/5, plus 3/5, which is 8/5, divided by 2, or times 1/2. 8 divided by 2 is 4. We should know the square root of 4, which is 2. So here's the answer. Rationalize the denominator to get negatives. I guess I'll put the negative in front. 2 times the square root of 5 over 5. And that is it. All right, so there's 2 Delta Math links to practice with the double angle formulas and with the half angle formulas. Good luck.